Okay, so we're going to talk about exponential growth and decay. It's a pretty important concept. It's probably one of the most important when it comes to exponential functions. Exponential growth describes things that grow exponentially, like population or bacteria multiplying, those kinds of things, and then things that decay exponentially or get decreased in an exponential format, so very rapidly. There are formulas for exponential growth and a formula for exponential decay. They are very similar. You need to make sure that you are taking notes as we're going through this video today. Please, please, please show up with notes tomorrow proving that you saw this video and that you know what's in it, so that I do not have to come up with an alternate assignment for you again tomorrow. So, exponential growth. Here is the function or the equation you're going to need to know for exponential growth. Here is how exponential growth is written. It's written as y equals a times 1 plus r to the t. Now I've got to tell you what all of this stuff stands for. A is the initial amount. So when you're looking at a problem and you are given a situation, A will be the original amount of whatever you were dealing with that you were given. R is the rate of growth. And T, you might guess, is the time. And so it's the time that you're dealing with in whatever problem that you have. So A is going to be your initial amount, R is the rate of growth, and T is the time. And as long as you have those three things, you can write an exponential growth equation from just about any problem that you were given. Now, exponential decay is how quickly something decays, and so it's dealing with things that are decreasing. So its function looks like this. Let's change colors here so you can see. Exponential decay is in this form. It is y equals a times 1 minus r to the t. So it's basically the same formula, only you have a minus instead of a plus. Everything means the same thing. A is the initial amount. So it's whatever you started with in your problem. R is the rate of decay. And T is the time. This is sort of like what y'all learned last year as 7th grade pre-AP students when you did the simple interest formula and you had the I equals PRT and you had to remember everything. You still have the R and the T, but now you have an A. But as long as you can remember these things, you can write a formula. And so that's what we're going to be practicing today, is writing equations for exponential growth and exponential decay. So let's do an example. We're going to do exponential growth first. The population of a city is increasing at a rate of 4% each year. In 2000, there were 236,000 people in the city. Write an exponential growth function to model this situation, then find the population in 2009. First thing we have to do is be able to write a function to model this situation. This is actually very important. People who study population growth and the things that are happening in our world and who say we're going to be out of these resources by this year, they do this using these kinds of functions because they know population grows exponentially and that this is the mathematical formula they use. So step one, we have to identify A and R. If you remember back over here, A is the initial amount, R is the rate of growth, because we're dealing with a growth problem here. So A is the initial amount. Well, our initial amount in this problem was how many people there started with in the city. Well, what we were given is that in 2000 there were this many people. So A is 236,000. I know that's a big number. It's okay. And then R is the rate of growth. Well, they tell you that it is increasing at a rate of 4% each year, but I cannot use 4% in a problem. I have to write it as a decimal, so you should all know that 4% as a decimal is 0.04. So now we're going to substitute for A and R into this function, the y equals a times 1 plus r to the t. We're going to substitute in the A and the R. So I'm going to have y equals, A is 236,000 times 1 plus r, which is 0.04, to the t. That's what the growth function looks like. That is the growth function that models this situation. Now they want you to substitute for t so that you can solve it. So I have y equals 236,000 times 1 plus 0.04. And now I got to substitute for t. Well, I'm going from 2000 to 2009. Well, that is a change of 9 years, so I'm going to substitute 9 for t. And then I'm going to grab my calculator. So I'm going to go over here to my calculator, and I'm going to type that in exactly as it is written, exactly what I just wrote down. So I have 236,000. Oops, too many zeros. Parentheses, because that's what I have written down, 1 plus 0.04, close my parentheses, to the power of 9. And I'm going to hit enter, and it's going to tell me the answer. That's all there is to it. You don't have to go get all fancy. Just use your calculator. That's what it's there for. Now, this comes out as a decimal. You have 335,901 point blah, blah, blah. I can't have part of a person. We're talking about population. We're talking about number of people. So this needs to be a whole number. So I need to round this off to the nearest whole number so that it makes sense. And so what I end up with is 335,902 people in 2009. So if you're going to label this, this is people. So that's how many people there will be in this city in 2009 if the population continues to increase at that steady rate of 4% every year. That's exponential growth. Now, exponential decay. We're still going to deal with population. This time our people are moving from our city at a very fast rate because they don't want to live there anymore, something bad has happened, there was an earthquake, I don't know, something. So the people are leaving this city in droves. But so the population of a city is decreasing at a rate of 6% each year. In 2000, there were 35,000 people in the city. Write an exponential decay function to model the situation, then find the population in 2012. We're going to start the same way. We're going to identify A and R. For this problem, A is 35,000 because that's how many people were in the city in 2000. That's the initial amount I was given. My rate is 6%, so that's 0.06. And I'm going to plug those in to that function that I had for exponential decay there. The only difference between it and the other one is that it has a minus instead of a plus. So I'm going to have y equals 35,000 times 1 minus 0.06 t. And I've got to substitute in for t. Go back to full screen here. I'm going to substitute in for t. And so I'm going to go up here. I'm going from 2000 to 2012, which is a change of 12 years. So I have the same function, 35,000 times 1 minus 0.06 to the 12th power. And I'm going to do the same thing. I'm going to go use my calculator. I'm going to plug that in, and I'm going to round to the nearest whole number because I'm still talking about people. I still have population. So after 12 years, if people are leaving the city at this rate, I would only have 16,657 people left in my city. So this one is exponential growth. It's when things are increasing at a specific rate. This one is decay, when you have things that are decreasing at a specific rate. And that's how you write the equation, and then that's how you use it. They just want you to find the equation of the function that is shown in this table. So you were given a table, and they want the equation of that function. I can find my constant factor pretty simply. It's a lot, but I can find my constant factor pretty simply by going through the table. I'm not going to do that. I'm going to go use my calculator, and knowing that we are studying exponential functions, that if I graph this, it's most likely going to be an exponential function. So I'm going to go to my calculator, just like I did a moment ago, except this time I'm going to go to Stat and Edit so that I can put stuff in my list. I have stuff in my list, so I'm going to go clear it out so that I can enter that information from my table. And so the table that they give me, my x values are -3, 1, 3, 4, and 8. And then my y values were 0.001, 0.625, 15.625, 78.5, 0.125. And then a really big number, 48,828. One moment. Apologize for that little interruption there with the announcement. So I've entered my values into the table. I want to go find out the function. So I go back to stat. I'm going to go over to calc, and I'm going to scroll down to exponential regression, which is the EXPREG. So it's 0. I'm going to hit enter, and I'm going to hit enter again so that it will give me my equation. Now, it gives me these big long decimals. I'm going to round for the sake of rounding for my problem. And I'm going to come over here, and I know that it's going to have to be a function in this form. Y equals a times b to the x. My calculator said that a was 0.125, 0.00 something, so I can round it to 0.125. And that b was 4.99999. I'm going to call that 5 to the power of x. So I'm going to round to make this fit better. Now, if you want to deal with fractions instead of decimals, 0.125 is exactly the same thing as 1/8 times 5 to the x power. They're the same thing. It doesn't matter which one that you write, but that is going to be the function for that stuff shown in the table. And if you were to go plot the points on your graph or plot the points on any graph and then draw this function over on top of it, they would match. That's what it would look like. So that's exponential growth and decay. You need to remember these two functions, these two equations, the a times 1 plus r to the t and the a times 1 minus r to the t. That's how you're going to have to be, you're going to need to know those so that you can write a growth function or a decay function depending on what you're given. So make sure you have those written down so that you can refer to them. And then I will see you tomorrow in